a lot to the organizers for the kind invitation. It's really nice you organize this workshop. So I'm going to talk about the path integral field theory approach to quantum thermalization. Okay. Let's see.
Maybe if you press OK, it's gonna just. I think it goes away.
Yeah. Okay, so I guess I don't have to motivate too much. We're interested in closed many-body systems, unitary dynamics of entangled quantum matter, being interested in.
It's not working then.
Jesus. Let me see.
So,
yeah, now it works. Okay, so being interested in questions like what are bottlenecks for entanglement spreading, what are conditions under which such closed many-body systems thermalize or not. We are interested in pre-thermal regimes, and all these are very challenging, interesting questions we try to understand. But then there's also a very practical aspect about closed many-body systems. We learned about yesterday also in the talk with Nikita that in the future we will have to somehow benchmark the output of, let's say, order 100 qubit quantum computers operating in the quantum supremacy regime. So where by definition classical simulation classical computers won't help us much. So this is all, at least for us, very much motivation to try and push forward analytical tools. The battery, no, I think it's fine.
Close to the computer.
Yeah, okay, close to the computer. So here I want to talk about a very specific analytic approach, a specific field theory approach to quantum thermalization. A field theory approach which already in the past has been proved to be very powerful in related topics. A theory that in principle allows you to capture microscopic dynamics and dynamics up to the non-perturbative long time regime. This statement hopefully becomes more clear throughout the talk. And a field theory that has played a very important role in our understanding of disordered and chaotic single particle systems in the 90s. And what we kind of dream of, or is to push this method to let's say a version 2.0 that allow us then to tackle challenges posed now by entangled quantum matter. And by we, I mean Joaquim Teles de Miranda from CBPF Rio, Kan-Woo Kim from Chung-Ang University, and Alex Altman from Cologne. And the work that I'm going to talk about has been partially published, is on the archive and in preparation. Yeah, so now I have to stay here. So let me start then with the systems that I will discuss throughout this talk. So there will be on one hand these brickwork models, so where you have some, let's say, L qubits sitting here, and then you evolve in time in the vertical directions by applying, in this case, random unitaries, single particle random unitaries, and two particle random unitaries. Then I will discuss or comment on briefly a work which corresponds to the, let's say, Hamiltonian version of this, where you have random, let's say, small quantum dots, which you can also describe by random matrix theory, which are capacitively coupled. And this corresponds then to continuous in time evolution. Now, these two systems I mainly will talk about have the property that in these cases you start out from, let's say, fully ergodic single particle systems. So these are described by random matrices where you do not resolve any internal single particle dynamics anymore. I will briefly comment on the work that we are doing now, which is related to coupled rotors, so where you still resolve internal relaxation dynamics, which brings an interesting new aspects to it. And as said, like all these theories that we usually look at involve some ensemble average. So this is motivated by the fact that, well, we are not interested in microscopic details. So we want to get rid of microscopic details and apply some, let's say, maximal entropy approaches, which technically allow us then to establish our methods. But thinking about maybe yesterday's lecture, this means that in most cases we get rid of all possible conservation laws. So it's a simplification, and we can later on try to implement more microscopic specific details. Now, the observable or computable that I will focus on in this talk is just a spectral form factor, but we also are looking into entanglement and operator spreading. I will just briefly comment on how this changes the approach. So then let me start out with, let's say, the ergodic phase of the many-body chaos. So as said, like in our case, we are looking at these, let's say, simplest versions where we have ensemble averages, which allow us to get rid of microscopic details in conservation laws. So in our case, this many-body chaos, let's say fixed point, this ergodic fixed point, for us is just a random matrix theory description. So this corresponds to some large random matrix in your many-body Hilbert space. And what we want to understand is how, starting from, let's say, some non-universal theory, how you thermalize, relax into this, let's say, ergodic fixed point, which for us is a random matrix theory. And as already mentioned, considering finite systems, we have a discrete spectrum. Like if you have some many-body system, you have some, say, slow collective excitations, but there is a gap which defines the time, the Thouless time, by which you typically then will flow into this fixed point if you have look at systems that actually thermalize. Right? So in our case, this ergodic fixed point, then we associate with the universal ergodic features of random matrix theory, meaning that we have the typical level repulsion. So the level statistics is described by Wigner-Dyson statistics, and the wave functions we can think of as random waves drawn from some Porter-Thomas distribution with nearly maximal entanglement entropy. So why do we like this field theory approach? Why do we insist on trying to push this forward? Is because we know, in a way, the field theory of this, let's say, ergodic fixed point, which for us is random matrix theory. So we know very well, understand very well the field theory that encodes all the correlations of random matrix theory. This is a matrix model with some nonlinear constraint. It's a version of the Wegener-Yefetov sigma model introduced in the 80s. So in this sigma model, you have the action, which has a coupling constant, which now, depending on if you're in the single or many-body context, so we are mainly interested in the single-body context, but as this is a theory for quantum chaos, you can also describe with this theory single-particle chaos. So this coupling constant is the density of states, or let's say the Hilbert space dimension of your single particles Hilbert space or your many-body Hilbert space. And then the main player in the game is this matrix field, the degree of freedom that you look at. And this matrix is structureless in Hilbert space, has some internal structure related to some causal structure, not so important. And for us, it's important that it's a b-local field in time. So if you have discrete time evolution, this corresponds for, let's say, t times that, it corresponds to a very large t times t matrix. And very importantly, it has this nonlinear constraint that the matrix multiplied with itself is the unit matrix. So this implies that this theory, although it looks quite simple, is actually a very rich theory which encodes a lot of, which has a lot of interaction due to this nonlinear constraint. So typically what you can do, so this matrix field lives in some group or coset space. So typically what you can do is you can parameterize these matrices by generators, like in an exponential e to the generators, and then expand in the generators. So what you have in lowest order is then a quadratic theory, which is a propagator of your theory. So in this case, as said, this matrix is structureless in Hilbert space, has some internal structure that's not so important, but it is bilocal in time. So expanding to quadratic order, we will have a propagator that now depends on 4 time elements, right? So it's 2 matrices that depend on 2 time indices, it depends on 4 time indices. So this propagator actually describes the following. So you can think of it as the combined propagation of a retarded and an advanced propagator that will undergo the same sequence of scattering events. So this is indicated here by this dashed line. So they follow the same sequence of scattering events. However, can do this in different times. Like the retarded propagator undergoes the scattering events in between from time t1 to time t2, and the advance from t3 to t4. So this is just indicate like in the advanced time evolution is contrast to 0. Okay, so then if you look at the propagator, so this is some let's say in a random matrix description, this would be like your states which you scatter from to the next. So if you then look at the propagator, this actually just implements causality. So it says that T2 has to come after T1. And then there is another constraint which tells you that the time the retarded propagator needs to pass through this sequence of scattering events is the same as the advanced. So this time difference has to be equal to this time difference. Then it's structured in Hilbert space and just weighted by 1 over the Hilbert space dimension.
Average over U when you assume.
Yes. 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 This is exactly like after averaging over U. So if we now want to get a better understanding, let's set one of the times to 0. Then this depends actually on the 2 times. So this is the time t you propagate. And then this delta t is in a way the offset of time by which the advanced propagator follows the same sequence of scattering events compared to the retarded. So if you would think of a classical theory, like classical diffusion or whatever, then these 2 amplitudes should be tied to classical probability, right? So in this case, the delta t would be equals to 0. This object would just describe some classical probability distribution. However, in the quantum case, these retarded advanced propagators can have their own life. So they can go through the same sequence, but at different times. And this is important because this then allows you to have a lot of quantum interference going on, which is encoded in this matrix theory in higher order vertex contribution. So you can expand this into 4, 6, and so on order, and then you can draw these nice diagrams. But in the end, these all describe quantum interference processes due to the fact that these amplitudes can somehow split and then recombine, so they encode quantum interference.
Are the generators of the algebra?
Yes, yes, yes. And there's some retarded advanced structure, which I just don't want to talk about because it's not so important. So let's illustrate this at the example of the spectral form factor. So in the case of spectral form factor, you calculate the ensemble average, the connected average of a trace of some propagator for time t. So you can think of it in discrete time evolution as the t-fold product of a unitary, and t times the trace over the product of 2 Hermitian conjugates. So we can draw this as a retarded propagator, which propagates in between time 0 and t, starting and ending at the same state as denoted here by the trace. So in the same way, we can draw the advanced propagator starting at 0 and t, and again from the same state. Now, what we said is in a classical case, you want to have this being a classical probability, so they would really start and end in the same state, go through the same, like synchronously through the same scattering events and stop. But since we have here a quantum problem, we have this kind of sliding degree of freedom of time, which brings the quantum aspect into it, and yeah, is the quantum, let's say, aspect to it. So it's like, let's call it a sliding degree of freedom of our time, which we have in the quantum theory. So this then means that the sigma model, when you calculate the spectral form factor, just exactly accounts for this fact. So you can draw now this diagram as two of these propagators, which encode the fact that the delta t can be shifted, this offset, from 0 to t to any value. Now the propagator just has to fulfill causality, so there's some 1 over d squared or whatever. But in the end, if you calculate this diagram, you will just accumulate, let's say, the phase space of this time sliding degree of freedom, which is between 0 and t. So you find that this diagram just gives you a term which is linear in t. So this is a linear ramp of the spectral form factor. Now, if you want to, and again, this delta t encodes in a way quantum interference. So let's keep this in mind. So if you just want to compare this to, if you apply, let's say, Weingarten calculus, then you would, for example, here t equals 2, you would draw your unitaries in this, let's say, tensor network representation. And if you do, then the average via Weingarten function, you cover the same. But in this Weingarten construction, you somehow construct these ladders, which in the field theory are already in the propagator. So it's in a way more, I would say, more economic, the field theory, but it's very much in the same spirit. So with this, we understand simply very easily the linear ramp in the spectral form factor of random matrix theory. Now, within the field theory context, this would correspond to a perturbative expansion in the generator. So this corresponds to what we would call the perturbative short times, where everything is dominated by some saddle point and some Gaussian fluctuations around the saddle point. So the saddle point has to do with some symmetry breaking in the causal sector. And the interesting part then comes once you go to times which are so large that you can resolve your discrete levels. Then something interesting happens, because the theory then becomes non-perturbative. So once you localize in given energy levels, in the field theory language, this means that you want to restore the causal symmetry breaking. You have very large fluctuations, and you actually cannot do your calculations anymore by some simple perturbative expansion, but you have to integrate over the entire manifold. So I think this is one of the things that we like about the field theory, that in any other calculation, this is very hard to go to this non-perturbative regime because it's non-perturbative. But within the field theory, you can do these kinds of calculations by explicitly integrating over the manifold. So, but this is all old story. This is like decades ago. This is describing, let's say, RMT correlations of, if you think in the many-body context of the fully ergodic regime. This is all very, very well understood. Now, what we want to understand is how you actually approach this RMT fixed point in the many-body context. But before coming to the many-body context, let me just illustrate how this would, for example, work in the single particle context. So how do you get single particle chaos RMT? So an example would be a diffusive quantum dot. So you have some confined particle in a confined region where you have disorder. So this confined region has some length L, which should be smaller than localization length, where Anders localization sets in, so that's very small. And we know the field theory for this problem. So this is our nonlinear sigma model as described before, only now in frequency representation. This matrix Q here now also has a space dependence, so it's not structureless in space. And then we have this, let's say, kinetic or diffusive term, which just describes the diffusion of the particle. So this would, in a way, be the non-universal theory. But now,
so this term is entering because now you have structure. So these derivatives are
yes, spatial derivatives, exactly. But now we can yes. It's gradient Q squared. Yeah. So, but if you write it in generators, it's quadratic in generators, everything. So you have your diffusion. Yes. So this is now very nice, because this here describes now diffusion in a confined region. So your diffusion, like the momentums are quantized, and you know that the minimal price you have to pay for inhomogeneous configurations is given by the diffusion constant over L squared. So this sets like your gap for inhomogeneous configurations, which now sets your time scale on which you relax to the RMT limit. So if you look at time scales much larger than this Thouless time, then you say, well, it's very costly to have these inhomogeneous configurations, you can just project this model onto constant configurations, and this term drops out. This matrix becomes only like frequency or time dependence, but we return to our RMT description that we had before. And this means that in the single particle context, we very nicely understand then the linear ramp and the plateau as discussed before, but this non-universal theory now tells you also what happens in this non-universal regime. What is the contributions of the diffusion modes to the spectral form factor? And we understand that approaching this, I shouldn't say ergodic here, it's single particle, how we approach this quantum chaotic fixed point by just relaxation onto a spatial uniform mode. So this is very, very nice, and we understand this. Now, what we have been fighting with a lot when we try to upgrade this theory to the many-body context is that there is a new aspect to the problem which was very hard for us to understand how to incorporate it. And this is that now, in the many-body context, we actually want to approach this many-body RMT fixed point. And this many-body RMT now lives in a Hilbert space, which is the product of the single particle spaces. But if you, for example, prepare your initial state as a product state and have weak interactions, then initially your dynamics will factorize, which means that approaching now this many-body RMT fixed point, there will be two important ingredients. It will not be only relaxation, but you also have to see how the degrees of freedom become entangled. And this entangling of the degrees of freedom, we found very hard to see how this appears in the sigma model language. And we could make progress to this, or we now think how this happens in the sigma model. So to explain this, let's look at a minimal setup. So this minimal setup corresponds to, let's say we have two qubits. Oh, I should also mention, like, so we have two single particle Hilbert spaces, and we always need that these single particle Hilbert spaces have large dimension. Okay, so that's one thing that's not so nice, but we need. So, and then you have this DEPS2 quantum circuit acting on these two qubits. So on this DEPS2 quantum circuits consist of individual random matrices applied to the single particles. So this is just creating single particle chaos in each of the dots, and then followed by some two particle operators. So this operates on the two Hilbert space, and this is parameterized by some interaction constant lambda. So in the simple case of lambda being 0, what we have is just the evolution of two RMTs in the single particle cases. So in a way, what we have is the complete factorization of the dynamics into the product of two single particle cases. So the propagators just factorize into the product of the single particles, meaning that in this case, you get a linear ramp for this spectral form factor and for this spectral form factor. So if you look at the many-body spectral form factor, this will be growing as t squared. So it's a random matrix theory, single particle random matrix theory, tensor product 2. But what we want to see is, once we crank up a little interaction, how this now relaxes into an RMT of the many-body problem. So an RMT now, which describes a random matrix that lives in the tensor product states of both. And our problem was to understand how this transition happens. So if you think about it, like we were fighting with it, we know exactly what this theory is. Without interaction, well, it's the sum of two nonlinear sigma models, which have as a coupling constant the Hilbert space dimensions of the individual spaces. Somehow we have to understand how the transition happens to the many-body RMT, where you now have a sigma model which has its coupling constant the product of the two density of states. And this was somehow very hard for us, but we could make progress. So here's now the field theory, and I try to explain like the main insight that we have. So this is now becoming a little technical, but I hope that the main message becomes clear. So we start out from a sigma model which has the RMT, describes the RMT of the single dot. So this is the single particle RMT of our systems A and B. And then for finite lambda, we have an interaction term. And this interaction term we did not really understand. But then one has to look a little bit better at the structure to understand it. So this has...
You're assuming that each, let's say, grain is fully structureless, so you don't
Yes.
have the diffusion part.
Yes, so that's always what I said, like in our case, the thermalized phase is structureless. It's RMT because we already, so you can understand like the structure of these, that there's two qualitatively different terms. So there's the so-called out terms and there's the in term. So the out term comes with a positive sign, the in term with a negative sign. And what they described, so the out and in terms also run under the name.
So if you did a simple expansion in small lambda,
Yeah.
diagrammatic.
Yeah. For what?
You are for trace of k, for k of t. Now k of t is at order 0 in lambda is the stuff.
It's a t squared, and then you should see that the t squared gets suppressed, and I'll tell you how it gets suppressed. Yeah, so it should get somehow suppressed on a rate which is the Fermi's golden rule scattering rate, and this is like the perturbative version of it. So I try to explain you. So the statement is there's decoherence going on, but it's not only decoherence. So
just confused because lambda disappeared.
the lambda is, sorry, yes, it's bad notation. The lambda is stored in the C0, CO, and CI. So this is the let's say, non-interacting part, and this is the interacting part. So these guys depend on lambda. Yeah, for lambda equals 0, this would be 0. Yeah, sorry, that's the bad notation. Yes. Exactly. So these are qualitatively different. So first we observe that the out terms come with a plus sign, the in term with a minus sign. They also run under the name self-energy and vertex correction. So I just give you now technically what they are, and then I try to give you some intuition. So the self-energy contributions are interactions between only retarded or only advanced propagators, and the vertex corrections actually are interactions between the retarded and the advanced. So they involve both causal structures. Now, I at least found very instructive doing some excursion. I hope this is not bringing too much noise into it, but this interplay between self-energy and vertex correction, I think, becomes bestly explained at some discussion which happened, let's say, some 20 years ago based on an experiment. So this is an experiment where the decoherence rate of electrons in disordered quantum wires was measured. So you have electrons propagating in disordered quantum wires interacting via screen Coulomb interaction. And this experiment just showed that as you go to lower and lower temperatures, something weird happens. This decoherence rate seems to saturate. You would expect that it just diverges for t going to 0, but it seems to saturate. So this led then to theoretical proposals which said, well, electrons in disordered wires interacting via Coulomb interaction can actually have 0 temperature decoherence. And that led quite to a big discussion, a theoretical discussion, which was based on this, everything based on this diagram. So this diagram depicts quantum interference correction to the classical conductivity, so-called weak localization correction. And this decoherence rate was measured by measuring this quantum interference. So this here would correspond to the electron or retarded advanced propagators. We can here say electron hole being tightly bound together, forming a classical probability amplitude, and here also. But here at this point, something interesting happens. So this is like diffusive environment. You can have returning loops in this diffusive system. And at this point now, we have a quantum system. You have this degree of freedom that retarded and advanced propagators are not classically bound together, but have their own life. So here, let's say the electron propagates along the loop in this direction and the hole in this direction. So this is, again, a quantum interference term, which gives you a correction to the conductivity. And this was measured in experiment. From this, the dephasing or decoherence rate was measured. Now, if you have interactions, this will lead to decoherence. So the simplest decoherence, well, you would say, is you have inelastic scattering processes. An electron interacting will change its energy states and will decohere due to the inelastic scattering process. And this is described exactly by this out or self-energy contribution. So this is a typical self-energy diagram which now tells that the electron is not living forever in an energy state, but can undergo inelastic scattering process. Now, all the complicated part here comes is if you would, for example, calculate this self-energy contribution for the electrons interacting via screen Coulomb interaction in the 1D system with this order, you would have to do an integral over the frequencies exchanged in this interaction processes over function, which is highly dominated by the low frequency contribution. So this integral itself is not well behaved because it's infrared divergent. This has to do with the screening in this disordered environment. So this means this is somehow a complicated object, and one has to see how you have to regulate it in the infrared. And this is where the vertex contribution come into play, because you also have the vertex contributions, which are now interactions between the retarded and the infrared. And they are very smart, because they now something very physically important, that if you calculate the decoherence rate due to this interference process, you have to recall that if the typical time for propagating through this loop is delta t, then actually fluctuations that occur on timescales that are larger than delta t are perceived by the electron as static. So they cannot decohere. So there is processes like physically where the fluctuations are on so low frequencies, on so long timescales, that physically do not make any sense. So if I calculate really the physically measured decoherence rate, then I have to take into account that bath fluctuations on very low frequencies actually are cut off and do not decohere, and this is exactly the vertex contributions which do this. So there's an important self-energy, cancellation of self-energy and vertex contributions, which tell you how to do the right physics. So now with this excursion, we can go back to our problem where we have like the two qubits interacting via this interaction term. So again, we have like now an interaction. This is like a general two-body Hamiltonian, which provides interactions. And we said that we have this self-energy and vertex out and in contributions. So the self-energy contributions just want to decohere everything again. So they want to, you have a classical decoherence rate, like that's just Fermi's golden rule decay rate, and they just want to decohere everything and make everything classical, like the delta t should be 0. But then you have to recall that there is vertex contribution, and they should do something important, because we know that in the entangled many-body system, there should still be an RMT mode surviving. So it's a closed coherent system. So it's true that the single particle RMT mode somehow decohere, but they have to decohere in a way that there survives a many-body coherent mode. And let's see how this goes. So let's recall that in the non-interacting case, we have just the propagators for system A and B, which decouple, and we have for each this kind of sliding time degree of freedom, delta T, delta BA. Now, the self-energy contributions just want to kill delta TA and delta TB. They want to decohere everything. But the vertex corrections, if you look at them, they are very clever, because they tell you actually the self-energy terms do too much, because there is surviving a many-body mode, and this is when delta P equals to delta TA, one can see in this expression that this does not decohere. So this means we have again like a very physical cancellation of self-energy and vertex corrections if delta TA equals delta TB, which then describes in a way the locking of the sliding degree of freedom of the individual systems, which would correspond to factorization of propagation, to a common value which describes now the locked many-body mode. And mathematically, this means there's some like Hadamard mode which remains phase coherent. And with this insight, we could then calculate actually. Sorry, I should go back to this. Yeah, so there's one like nice thing. Like technically, the locked many-body RMT mode now corresponds to the product of these two theta functions, which are completely equal because they are locked. And then you have the product of the two dimensions, which then give you the dimension of the total Hilbert space. So this is how technically you see that this all works out. Yeah, so then that was in a way the main message. Now with this, we can now really go down, sit down and calculate, for example, the spectral form factor for this two particle problem. So in the non-interacting case, the spectral form factor is just t squared. In the strongly interacting case, you just see the linear t. And this is now actually fit parameter free comparison between the analytic calculation and numerics for small values of lambda. So this works very nice, and I could comment on this structure here, which is important to that we are able to describe this non-positive long times, but let me skip this for the moment.
Is the like quote unquote ballast time here just 1 over d?
So we come to this, yeah. So yeah, so it's let's see it in the yeah. With this, we can then, generalize this to this brickwork model, where now, like, what we really want to have is like this array of L qubits or L qudits, which are measured in this brickwork fashion. So this is, again, always establishing for us a single particle chaos, and then we have alternating interactions between nearest neighbors, which will propagate the interactions to the system. So now, based on what we said, is we can understand then this as a problem where through the interactions, the sliding degree of freedom, which in this discrete time evolution is just a discrete set, is actually on neighboring side wants to get locked to the same mode. So we have the sliding degree of freedom for each of the dot, and this by the interaction wants to get locked. So if we look at the spectral form factor, we can see that this is just the partition function of the t-states Potts model. So we have exponential suppression by the decoherence rate in time whenever configurations on neighboring sites are not locked to the same value. So the spectral form factor just reduces to the Potts state model. And this is what also Chalker had derived previously. So we, in a way, re-derived it from we re-derive it within the field theory. I think, yeah. And this is now the comparison between numerics and the analytic prediction, again, parameter free. So at very weak interaction, we have the t to the L, decoupled spectral form factor. At long times, you have the t, and then there is some exponential decay now by the Thouless time, which increases logarithmically in the system size. So the Thouless time here is 1 over Fermi's golden rule, decay rate times. So this would be like the answer in L equals 2, this would be 1 over gamma essentially. And in an L qubit system, it's logarithmically in L. So then with this, we can also now address the Hamiltonian system. So we have random matrix Hamiltonians for the single particle systems, which are now capacitively coupled. And the important thing is now we have continuous in time evolution, meaning that we have energy conservation in the system. That means we have a slow diffusion mode in the system. And technically what we see is that in the discrete time, we have this kind of Potts model, which takes into account that time only occurs in discrete steps. So our, let's say, locking is described by this Potts model action. Now, once we go to continuous time, this discrete function becomes a continuous function. This, let's say, sliding degree of freedom is not changing in the discrete way, but is a continuous function. So this here gets substituted by some function which measures the sliding degree of freedom on neighboring sites, but is continuous. So this would be 0 when the difference is 0. But in general, it can be like it's a function that is 0 for 0 and gets finite for some finite difference. So this means that in a system with energy conservation, we in a way have now this soft mode which describes the small deviations in the sliding degree of freedom across the system. So for not too long times where we can still think of this, that the mode can adjust nicely, we can do some gradient expansion in this function and derive its spectral form factor, which is t times, and then let's say the partition function of a string, which just describes like this deformation of time soft string with a string tension, harmonic string with a string tension, which is given by the dephasing rate times the time. So this works for not too long times. At longer times, you have to take into account that this mode also is quantized. So it will, like in the diffusion problem, will relax to some constant. And then we get at this prediction for the spectral form factor, which now, due to the presence of the slow mode, has this algebraic decay with t to the minus L half, which is this slow mode in the system. And this, again, comparison with numerics. Here we had to have one fitting parameter because in a way it's very hard to describe this how the system gets locked, because this has to do with very short times, and this is we extending in a way our regime where our theory applies, because we have to somehow now mix short and long time. So we have to it's not so clean in this case as in the discrete time model, but at least we get from this a Thouless time that now algebraically increase power law decrease with L squared, as you would expect for a diffusive system. So let me see. I'm sorry. So this is like more or less the main story that I wanted to talk about. Now we can also just as a comment, we can also address operator spreading and entanglement, increase entanglement entropy by providing an additional replica structure to this matrix field. And then one has to look at the corresponding, let's say, locking of replicas. It's not, the locking doesn't occur so much in time, but it's locking of replica channels. But this is under control. So that's one thing that we are doing. And then comes the second part that we are working right now on. This is to try to incorporate the dynamics in the single particles system. So far, in a way, we concentrated on weak interactions or very fast particle relaxation, such that, in a way, our single particle Thouless time was always 0, so that we had to see how these fully relaxed single particle systems entangle. But if you crank up the interaction a little bit, you will reach a region where this interaction strength, or the rate for interaction times the single particle Thouless time becomes larger than 1. And that's quite interesting. That's something that, for example, you cannot address within this Weingarten calculus. And that's what I said in the very beginning. So in principle, we can introduce some more microscopic dynamics. So now something interesting happens, because this gamma will now entangle the system. So we'll do this locking in at times where the single particles have not fully relaxed. And in a way, it will then make you will make some crossover from single particle relaxation to some relaxation in some high dimensional many-body Hilbert space. And so there's some rich interplay which we are trying to understand right now better. Yeah, with this I come to the summary. So I tried to explain why we really want to push this field theory method to describe the challenges of entangled quantum matter. We really like our sigma model because it captures all the RMT physics. We now think we understand in a way how this ingredient of entanglement has to be introduced into the model. So this allowed us to address, let's say, relaxation measured by the spectral form factor for this brickwork and this models. We can also look at operator spreading entanglement dynamics. And yeah, so I got really enthusiastic about the talk by Nikita on yesterday, because I mean, that's something what we really would like to do, that we can provide some at least analytical estimates for, let's say, how the fluctuations of the autarch decay, like the power law, whatever, which you cannot calculate by simulations, classic simulation, but you then can compare to quantum computers operating in the quantum supremacy regime. So that would be something that we really would like to do. And with this, I would like to thank Saint Piquet and Farpege, Brazilian.
Okay. So thank you very much. Time for questions.
Yeah, it should work.
Thank you very much for a very interesting talk. I have a kind of naive question, like comparing these two, Hamiltonian evolution and Floquet evolution. So I can go from one to another if I increase the Floquet period and say that at each step I have totalization very small, unitary is close to unity. Can you describe, or maybe do you understand, or can you describe how this collective mode emerges and then exponential decay of the peak replaced by this power law decay?
Yeah, that's how you make the let's say the transition from the Potts model to the string. Yeah, so I mean, that's a little bit the problem that we were fighting with, is that when you let's say the Potts model derivation is very clean, so we do not have to do anything. Now, when we look at the continuous and time evolution, we have this function that wants to penalize slow deviations from, but we do not really have analytic control over this function, because this now has to do with very short timescales, which are beyond our effective description. So we cannot really, in a clean way, do this transition. The only thing that we can somehow say is that, well, if you're still at, let's say, intermediate times, there should be a regime where you can do some gradient expansion in this function, if it's a continuous time, and then you get at the string model. But to really see how to derive this from the Potts model, we would have to understand exactly this function, and that's, yeah, it's a weak spot. Yeah, you actually pointed.
With chokers at the approach gradients with this.
But they don't. I mean, have the continuous in time, right? Yeah. No. Yeah. But it's we have been fighting with this a lot, and at some point we just gave up. I mean, we cannot teach the model how to address the short time scales in a controlled fashion, and we have to do some hand waving.
Here, qualitative from exponential to.
Yes. So there's this power law intermediate regime. Yeah.
More questions?
But like if you go to very long times and you see that the string again has like quantized momentum, then it's like again exponentially named or whatever. Yeah.
More questions? Okay, if not, I can probably ask a question, because I remember when I read long ago the paper by Choker about the Floquet part. I was wondering what happens if one take a unitary that is not thermalizing. Now you have the Hamiltonian. So have you tried to replace the single grain Hamiltonians with like Rosenzweig-Porter and
No.
Do you think it's doable or is out of reach? Because I think in the Rosenzweig-Porter, because do the transition.
I can tell you what I would really like to do. So first of all, you have to introduce like in the coupled rotor system. So now you can resolve the single particle dynamics. So what I said is, like, if you crank up the interactions and then somehow you have the entangling before the single particles relax, and you have relaxation then in high dimension space. What I really would like to do is to go into the opposite limit. So you go now to the regime where your single particles relax, but you are already like localized in your, like you're beyond the single particle Heisenberg time.
Yeah.
And then want to see how entanglement happens there.
I see.
I want to do this for this coupled rotor system.
Okay.
And this is then like going more in the direction you want to do. And that's like, I don't know if this is possible, but that's like the cool thing, at least in this method, we have these non-perturbative long times. So now you can start wondering, how is entanglement happening if my single particles are localized in the single particle state.
Okay.
Right?
Yeah,
I don't know if you can do it, but you can at least try it. Yeah. I think that's, yeah.
Other questions? Okay, if not, we can thank Tobias again.
So as usual,